All right, welcome to this explainer. Today we're going to unpack the terrifying, chaotic 60-second descent of a massive ship sliding down a slipway. You know, if you've ever watched a traditional ship launch, it just looks completely out of control, right? I mean, it's a colossal structure of steel basically plunging backwards into the water. But as we're about to see, every single fraction of a second in that descent is governed by incredibly precise physics and really rigorous engineering.
So let's dive right into this. There's this great observation from the naval engineering world that says there's a moment during every traditional end launch when the ship appears to be about to trip over its own bow. It is calculated chaos. And that really hits the nail on the head, doesn't it? When you watch one of these launches, the stern goes in first, and there's this very specific, kind of terrifying moment where the bow is still stuck on the slipway, it pivots heavily, and the whole ship looks like it's just going to tip forward into a complete disaster. But it's an illusion. It is a meticulously engineered event. Because honestly, getting this calculation wrong can literally sink the ship before it ever reaches the open sea.
Section 1. The Launch Illusion. 60 Seconds of Danger. We're going to frame this entire explainer around this one exact concept: how engineers manage to avert a catastrophic structural failure in the span of just 1 minute. Because the launch is, without a doubt, the most dangerous moment in a ship's entire life. To really grasp the stakes here, I want you to just picture a number: 10,000 tons. Try to imagine that scale. You've got 10,000 tons of steel resting entirely on this temporary cradle. The whole weight of the vessel has been shifted from fixed building blocks onto a moving cradle that sits on groundways coated with a lubricant. And historically, that was actually a mix of tallow and soft soap. Yes, literally soap. So that incredible, massive weight is balanced purely on a slippery track, held back by a set of triggers just waiting to violently move under the sheer force of gravity.
Moving on to part 2. 3 phases of launch, down the ways. Okay, let's slow down time for a second and break this dramatic 60-second sequence into its chronological steps. The traditional end launch happens in 3 distinct phases. Step 1, the mechanical triggers release and the ship immediately starts accelerating down the inclined ways, pulled purely by gravity. Step 2, the stern of the ship actually hits the water. At this point, buoyancy kicks in and begins acting on that immersed stern, which partially lifts the back end of the ship. And finally, Step 3. As more and more of the hull slides into the water, that upward buoyant force gets stronger and stronger until the hull literally tips on its forward supports, which are called the forward poppets, before it finally floats completely clear.
Section 3. The tipping moment danger, pivoting on the poppets.
Now, I want to freeze the action right at phase 3, because this right here, this is the exact moment of maximum danger. It's known as the tipping moment. It's this incredibly critical point where buoyancy partially lifts the stern, causing that heavy hull to try and pivot forward on those forward poppets. Think about it. If the bow rises too sharply before enough of the hull is actually supported by the water, those forward poppets are going to be completely overloaded. If those timber and steel supports collapse, or honestly, even if the ship just pivots at too steep of an angle, the steel hull itself can snap or suffer massive structural damage.
So what's really happening here is basically a massive high-stakes tug-of-war. On one side, you have the buoyancy force acting at the stern, pushing upward with immense power. On the other side, you have the sheer weight of the ship, pushing downward at the center of gravity. And caught right in the middle, acting as the ultimate pivot point for all of this kinetic drama, are those forward poppets.
Part 4. The Crucial Launch Calculation, where math is basically the hero. You might be wondering, how do naval architects guarantee this giant structure doesn't just snap in half or crush its own supports? Well, they plot out 2 moment curves against the distance the ship is going to travel down the ways. And the absolute, non-negotiable, critical rule here is that the weight moment must always exceed the buoyancy moment right up until the ship is fully floating. If the buoyancy force somehow overtakes the weight force before the ship is fully supported by the water, the bow rises catastrophically, the whole launch becomes fundamentally unsafe.
But engineers don't just, cross their fingers and hope for the best. They actively control this math. To prevent those lines from ever crossing in the danger zone, naval architects meticulously adjust 3 specific variables. They tweak the cradle design to alter exactly how the ship's weight is distributed. They change the ship's starting position on the slipway. And, amazingly, they precisely formulate the exact friction coefficient of the lubricant on the tracks. By dialing in these 3 factors, they basically force the physics to guarantee a safe entry.
Section 5. Acceleration and water entry. Let's talk about kinetic energy.
So with the math checked, the curves perfectly plotted, and the tipping disaster totally averted, let's follow the energy shift across this crazy 60-second window. At 0 seconds, the triggers let go. Gravity absolutely dominates, accelerating the ship down the ramp. Then, around the 30-second mark, as the stern digs in, water drag and resistance rapidly start building up, fighting against all that acceleration. By 60 seconds, the buoyancy force finally balances out the pull of gravity, and the ship is fully waterborne. But it is definitely not sitting still.
At the exact moment of full water entry, this colossal steel structure hits its maximum velocity. We're talking 3 to 5 meters per second. That means you've got 10,000 tons of steel tearing into the harbor waters at over 10 kilometers per hour. Which, okay, might not sound like highway speeds, but for a skyscraper made of solid steel, that is incredibly fast.
Which brings us to a frankly urgent reality. 10,000 tons of steel is now carrying massive forward momentum directly toward the far bank of the harbor. The ship is finally afloat, right? It's completely safe from the tipping moment that we were sweating over on the slipway. But all that kinetic energy hasn't magically disappeared. It's now carrying the ship straight across the water.
And that leaves us with one final, massive physics problem to ponder. The ship is moving at 5 meters per second, barreling right toward the opposite side of the harbor. Think about the sheer arresting forces required to safely bleed off that much momentum without ripping the ship apart. It's an unbelievable engineering challenge. So, how on earth do you stop 10,000 tons before it crashes?